Well, this time I hopefully have left myself enough time to get finished with this video. So let me continue on where I left off. We just had finished example 6. And the thing that was interesting at the end of that example was the number we ended up with down here in the answer. Even though I started with complex numbers, it ended up as being a real number with no imaginary parts to it anymore. So let's take a look at a couple of ideas here that kind of relate to that. Some of the work we've done with radicals, we figured out ways of what's called rationalizing the denominator. So with this first one, to rationalize the denominator, we multiply by the number 1, written as the square root of 3 over square root of 3. And when you multiply straight across, square root of 3 times square root of 3 is just 3, and then 5 square root of 3 in the numerator. The other one's a little trickier. If I just multiplied by the square root of 5, that would make this go away, but then this would have a square root of 5 with it. So what you have to do is you have to multiply by what's called the conjugate. And the conjugate is, I need to slide everything up here because stuff fell off the bottom of the page. The conjugate is this number, but written with a different sign. So instead of writing 2 minus square root of 5, I'm going to multiply by 2 plus square root of 5. Now notice this is still the number 1, but I'm choosing what's called the conjugate of the denominator. And so 2 minus square root of 5, and I'm going to choose to multiply then by 2 plus the square root of 5. Now when you multiply a binomial times a binomial, you have to FOIL. So in the denominator, I'm going to FOIL these things. So I'm going to take 2 times 2, that's where the 4 comes from. Then I'm going to take 2 times the square root of 5, get 2 square root of 5. That was the first, the outer. Now the inner, negative square root of 5 times 2 is negative 2 square root of 5. And then the last, square root of 5 times square root of 5 is just 5. And it's positive times a negative, so you end up with a negative in the answer down here. But now notice what happens in this middle term. You get plus 2 square root of 5, and then you got minus 2 square root of 5. They, of course, cancel each other out. And what I'm going to end up with then is just, and it fell off the bottom of the page, so let me rewrite it. In the denominator, these guys cancel out, and I get 4 minus 5, which is just negative 1. And so then I can take, well, so the thing I want you to notice is that the denominator ended up not having any radicals in it whatsoever. So I'm going to now take 14 divided by negative 1 and get negative 14, and 7 square root of 5 divided by negative 1 and get negative 7 square root of 5. So I have rationalized the denominator of this original problem back up here. So how does that work with complex numbers? We're going to use the idea of the conjugate. The conjugate of a plus bi is a minus bi. Just like a minute ago when I had 2 plus the square root of 5, I multiplied it times 2 minus the square root of 5. Well, that's what's going to happen here. I have 3 plus 4i in the denominator. I'm going to multiply it by 3 plus 4i. And look what happens when I FOIL that all together. So when I distribute in the numerator, because you multiply fractions straight across, right? Let me change the color here. When I multiply straight across, 2 times 3, 2 times 4, I have to distribute it. That's where I get 6 and 8. But in the denominator, I have to FOIL. 3 times 3 is 9. 3 times 4i is 12i. But then negative 4i times 3 is negative 12i. Those two terms cancel out. The O and the I will always cancel out when you FOIL with conjugates. And then the last term, when I take 4i times 4i, one of them's negative, one of them's positive, so I'm going to get negative. 4 times 4 is 16. I times I is I squared. But I squared is negative 1, so this negative 16 becomes positive 16. So this becomes 9 plus 16. That's how I end up with 25 in the denominator. Now you'll often be asked to write these in the form of a plus bi. So this fraction, understand what's happening. The 25 is dividing the 6, but the 25 is also dividing the 8i. Now I can write, when I write these as a fraction, I get 6 over 25, and I could write it as 8i over 25. but that's just multiplication. So I can pull that multiplication apart and have it as 6 over 25, and then 8 over 25 times I. And so just simply set this I out here, because you could think of it as I over 1, which is why the I is up in the numerator up there. Let me give you one more of those to try, and we'll do that together, because that's a little trickier. So if I had 3 over 6 minus 2I, well, the conjugate of the denominator is going to be the same numbers, but with the opposite sign. So I'm going to multiply by 6 plus 2I over 6 plus 2I. That's the number 1. So I'm not changing the value, I'm just making it look different. So in the numerator, distribute. 3 times 6 is 18, plus 3 times 2 is 6I. In the denominator, when I multiply, I'm foiling. 6 times 6 is 36. Look at the outside terms. Positive 12I. Look at the inside terms. Negative 12I. They cancel. The last term is going to be negative 2I times plus 2I, so that's negative 4I squared. But I squared is negative 1. And so negative 1 times negative 4 is positive 4, so the denominator is going to become 40. So let me pull this apart. I'm going to have 18 over 40 plus 6 over 40. The I could be in the numerator, but you typically write it out here as a multiplication. I would always want you to reduce if you can. Let's see, 2 goes into each of those, so that would be 9/20 plus 2 goes into both of those in front of the I, so that would be 3/20 I. And that's the answer to this division problem. So one last little thing that's kind of interesting about the number I. If I have I to the first power, you of course just get I. If I have I to the second power, we already figured out that that's negative 1. But look what happens when I have I to the third power. Well, I to the third power, I could think of that as I squared times I. Now I already know that I squared is negative 1, so I to the third power is actually negative I. I to the fourth power would be I to the third power times 1 more I. So I to the third power, I know, is, let me go back to that, sorry. I to the third power, I know, is negative I times 1 more I. That would be negative I squared, but I squared is negative 1, so negative 1 is 1. And a different way of thinking about that is to do this. Let me pull these up a little bit, see if I can get the stuff that dropped off the bottom. There we go. So I could think of I to the fourth power as I squared times I squared, and each of those are equal to negative 1, so you just get 1. So look what happens. When I put 4 of them together, the answer comes back to 1. So if I had I to the fifth power, I to the fifth power would be I to the fourth power times I. And I to the fourth power we just figured out is 1, so 1 times I is just I. What if I had I to the 23rd power? Well, every group of 4, if I wrote this out, I times I times I times I times I 23 times, every group of 4 would give me 1. So when I multiply the first 4 i's together, that's equal to 1. Now multiply the next group of 4 together. That equals 1. Multiply the next group of 4 together. That equals 1. And do you see that 4 goes into that 5 times? So the first 5 groups of I times I times I times I, that's 4 of them, the first 5 groups would just be it would be 1. And what that leaves over then is 3 i's at the end. In other words, look, 4 goes into 23 5 times with 3 left over. And back here we figured out that I to the third power, is just negative I. So without really doing a lot of work, the shortcut is, how many times does 4 go into this number, and then what's the remainder? And the remainder in this case happens to be 3, not necessarily the last number. What if it was I to the, let's say the 51st power? Well, 4 goes into 51 4 goes into 51. If I divide by 4, 1 times 4 is 4. Draw the line, subtract. That gets me 11. 4 goes into that twice. And so that's 8, and that leaves 3. So every group of 4 of the i's, every group of 4 i's would just be 1, and so then it would end up as I to the third. So this one also would be negative I, because back here we figured out that I to the third power, whereas I to the third power was negative 1. Well, that's complex numbers. There's a lot going on there. I hope this helps. We'll talk about it more in class.